Welcome to Group 37's presentation titled Contact-GraspTransformer, an enhanced grasp prediction model. Our work is broadly motivated by how the human brain can produce multiple outputs such as grasping and object recognition from the same input. So as the visual scene enters our brain, it first enters the early visual cortex, and then visual processing gets segregated across two separate pathways: dorsal known for supporting actions such as grasping, and ventral responsible for supporting perception such as object recognition. These pathways are shared early on in the brain, but as we move to higher areas, they get more segregated. This suggests that early features for object recognition might be useful for grasp learning as well. Deep learning has been pursuing object recognition and grasping for long, and we've been able to achieve human-level object recognition. However, grasping remains a challenge in the field. So here we're trying to offer a framework for better grasp learning inspired by the brain. And in this framework, we first try to implement a modern grasp prediction model and further test if we can integrate low-level features useful for object recognition to enhance grasp learning.
To look back at the history of robotic manipulation, we have classic approaches which are mathematically grounded but requires perfect perception. And then there are deep learning methods which uses CNN on 2D images and depth maps to generate grasps. But there are very limited to top-down approaches and won't work well in cluttered environments. And then there are modern era where we have 3D point clouds to generate 6-star grasps in cluttered environments. To train our model, we built our dataset on two main sources. One is ShapeNet, where we have 3D meshes, and then ACRONYM, which has 3D grasp poses for all these objects. We took RGB depth images and convert them into point clouds, and especially sample only 4096 points and feed them to the model, and then model predicts 6-star grasps on these point clouds. And to make this model invariant to different viewpoints, we augment the data with different camera poses.
So for our baseline, we try to implement Contact-GraspNet, which takes input point clouds and it feeds into a PointNet++ backbone, which consists of set abstraction and feature propagation layers with unit-style skip connections to preserve spatial information. And these have fed into 4 output heads. We'll come to these heads later in the presentation, which you can use to predict a grasp pose. But the set abstraction layers of PointNet++ contain k-nearest neighbors and farthest point sampling, which are known to be slow and have a limited receptive field, which is not good for grasping. So we turn to point transformers V3, which are known to solve the problems with k-nearest neighbors and farthest point sampling. They are known for its efficiency with both memory and speed. And this was a natural choice. We get rid of the slow PointNet++ and slap a transformer, and we solve our problems. So our proposed architecture consists of having this PointNet++ backbone, but we achieve it through voxelization of the point clouds. We now have these small voxels as tokens to the transformer, and we arrange these voxels into a 1D sequence by means of a Hilbert curve, which is a space-filling curve. And we also have grid window attention for the encoders and decoder layers, which have a conditional cross positional encoding at the start, and then your regular pre-norm and multi-head attention and pre-norm and feed-forward networks. So the grasp transformer, after passing through the backbone, will go through its output heads, which are 1-by-1 convolutions. It will predict the probability of a grasp at the contact point and also produce 2 vectors for the gripper's orientation and also the gripper's width.
To evaluate the model, we have 3 metrics. Contact point classification, where binary cross-interface loss is used to evaluate between the predicted and ground truth contact points, and then grasp quality, where we have 5 reference points used to compare against the ground truth gripper points, and then grasp width to penalize wider grips to encourage tighter grasp. For baseline, we trained the PointNet backbone and compared against the point transformer backbone. We could see that point transformer outperforms PointNet backbone. We run a ton of ablations, and during earlier runs, we suffered from gradient explosion. Then we addressed using gradient clipping. Unlike CGN, we use only single object point cloud and not multiple objects. Horizontal grasp failed due to the chosen gripper configuration. The point transformer V3 can take more point clouds, but we limited the size of point clouds. We have physics sim set up to evaluate the quality of grasps.
So we successfully implemented and enhanced a modern grasp prediction model using point transformer. And next, we're going to move on to integrating object recognition features with grasping.